Welcome again to the NPTEL course on storage systems. In the previous classes, we took a look at the disk as a device. We also looked at how a computer system can interact with a disk through a protocol called SCSI. That is what we looked at the previous class. Now, there are various ways in which the same protocol, SCSI protocol, can be used to interconnect multiple devices and with applications. So, we will look at, there are two possibilities, something called a storage area network, something called a network attached storage, and there are also other models like distributed storage. So, we will look today at some aspects relating to storage area network, and then we will look at network attached storage, and later we will look at how distributed storage models work. So, for storage area networks, we can use the SCSI protocol. As I mentioned before, the SCSI protocol usually in the beginning when it was initially designed, it was meant to be running on an electrical, let us say, transport, you might call it. And the idea here is, if I am going to make multiple devices, multiple disks or multiple I/O units communicate using SCSI protocol, you might need the electrical connections might be problematic for longer distances. So, the idea is to see how you can do it better. So, normally the problem with electrical connections is that, for example, if you have 32-bit transfers, you need 32-bit electrical lines, 32 electrical lines, and these, there's a problem called clock skew, so which creates problems. Therefore, what people like to do is to go for serial protocols. Now, what we want to do is to take SCSI protocol, encapsulate it into a serial communication medium, and then interconnect things. So, that is one way to do it. Other way to do it is to think of not at the SCSI level, but at the file level. You think of the application talking to the storage system at the file level, not at the block level. So, if you are using SCSI, you are essentially going to be doing it at the block level, whereas if you go to a slightly higher level protocol, the file protocol, then basically that is going to be using these lower level, possibly SCSI kind of protocols to access it. So, there are two different types of ways of accessing it, and we would like to look into each of this in some detail. So, what I will do right now is to briefly summarize the difference between these two and then proceed with discussing how fiber channel protocol enables you to encapsulate SCSI commands. So, essentially again to summarize, if you want to make storage systems scale to larger sizes, then you can have what is called network attached storage or storage area networks. So, the unit of access for network attached storage is file level, for the storage area networks at the block level, and it has got some implications otherwise also. For example, in sharing, it turns out that network attached storage typically can support multiple clients because it is a file protocol. So, usually there is a file system involved. Because the file system is involved, the file system can take care of concurrent accesses. For a storage area network, typically it supports a single client. If you really want to make it handle multiple clients, then there has to be something elsewhere, either at the application level or somewhere else, that has to handle concurrent accesses. Okay. It is basically has a simple idea that I block things, and therefore there is no other party in between. Okay. So, the machine directly talks to the storage. Okay. So, these are two differences. We will look at network attached storage later. Okay. One thing I should mention is that both this network attached storage and storage networks start around the same time. Okay. For example, network attached storage started about the early 1980s, and storage networks started close to later 1980s. Okay. For example, IBM came up with their first model, and later to eliminate, let us say, there's some, to standardize basically the fiber channel kinds of protocols for device. Again, just to give some background, it turns out that if you look at any protocol stack nowadays, an efficient, high speed storage protocol stack, the physical layer is almost always the same. It is still fiber. Either it's fiber or copper. You can't use copper for long distances. So if you have thinking about longer distance, it has to be fiber. And this basically means that you are able to transmit at optical speeds or basically at the speed of light. Okay. So it's extremely fast. Okay. But that means that since you are exchanging photons, it means that when it comes to your electrical circuits, because finally your computer system is built of electrical circuits, that photon has to be converted into some kind of particles or whatever that interact with electrical systems like electrons. So there has to be some converters between photons and electrons. Okay. That is something to be done here. Okay. So at the lower level, it's always fiber, and then there are some converters from photons to the electrical signals. And the upper level protocol is also typical always SCSI. This SCSI has become standard. Okay. That means that the lowest level and the topmost level both are standardized. So the in between things are finally going to determine exactly what's going to happen, because both are identical. The top level is identical, the lower level also identical. So what are the in between things that actually are finally determine the price and the, let us say, the performance of the system. So various protocols have been attempted in the past. For example, I will not go into it, but this has been attempted, something called SONET. Now fiber channel has been quite heavily used in enterprise systems. You will see that with the speeds of gigabit Ethernet, etc., and higher speeds like 10 gigabit Ethernet, this also has become very attractive. And there is also another model called InfiniBand, which was devised as a what is called a system interconnect. That means connecting CPUs, not necessarily storage. So this has been also been attempted to be used to interconnect storage and multiple storage units along with to the computing engines. So there are various possibilities. So what's interesting to also notice is that broadly there are two types of interconnect models. One you might call the telephone model, the other one you can call internet model. In the telephone model, typically you come up with what are called virtual circuits, and they usually typically give you guaranteed service. There is pre-allocation and reservation of bandwidth, and this is typically followed in models like fiber channel and InfiniBand. There is also an internet model which basically attempts statistical multiplexing, for example, gigabit Ethernet or 10 gigabit Ethernet. Okay. So the idea here is there is no notion of guaranteed service or pre-allocation reservation of bandwidth. Now in storage, it turns out that these things are quite important, guaranteed service and if possible bandwidth, etc. Because if you are trying to do, for example, backup and those kind of things, they are heavy duty and you cannot really depend on statistical multiplexing to bail you out all the time. So it's very important for you to do this. That's why for a long time fiber channel and those kinds of protocols have been reasonably predominant. I think with if 10 gigabit Ethernet becomes low cost, or you have something called metro Ethernets, where you have Ethernet at speeds of multiple gigabits within a city, those things become possible, widely possible, then again models based on gigabit Ethernet can also become extremely popular. Now the kinds of things that you do, either go for the telephone model or internet model, you have to actually do lots of other things that go with this particular characteristics. For example, I will just briefly mention one thing, the flow control. Okay. It turns out that the flow control of each of these kinds of models is different, and your performance or your controls that you need in your system depends on the kinds of flow control that is there. For example, you can do flow control for these network systems, network storage systems at the link layer itself, or you can do it at slightly higher levels, or even at the application level. Okay. For example, at link layer, if you look at gigabit Ethernet, it does it at something called MAC control sublayer. So, if it turns out that you can actually control the rate at which somebody is sending information by saying that the recipient party can say, I cannot handle your speed, please pause. And it tells you in terms of some nanoseconds. It tells you, for example, please pause for so many nanoseconds before sending it again. Okay. There is also something called credit based, where you can send only so many credits of data. Okay. For example, you might decide beforehand, the initiator and the target can decide there are going to be 64 credits or 256 credits, and then every time an ACK comes, then your credit increases. Every time you send data, you decrease your credit. Okay. That means that the throughput is determined by the round trip, because you have some credits in the beginning, you send it, and the other party has to ACK it. Then only you get one more credit. For example, you start with 256. It's true that you can send 256 packets in the beginning, but after that you have to wait till you keep getting ACKs. Once you get each ACK, then you are allowed to send one more packet. Now, if you have this credit base, that means that you really have some reasonable control over how the network is going to behave, but at the same time it creates some problems with respect to the throughput. We will discuss it later, why that is the case. Okay. We already mentioned that in the previous class that in SCSI you have an ability to control the flow. Basically, you have this notion of ready to transfer, and by which you can do it. Sometimes it is also the case that you encapsulate any of these protocols through TCP or some such thing, because you really want to access internet scale systems, and across internet typically TCP is only the thing that is available right now. So, it means that you need to encapsulate whatever protocol you have, either fiber channel or whatever, through TCP, and it also does its own flow control. Okay. Again, we will discuss this more extensively in the next class, where we talk about how TCP does it and how storage protocols based on TCP IP, for example, how they perform. Okay. So, all I wanted to mention here is that you can decide your physical layer, but still there will be some other layers that need to also are in the picture, and they will also do certain different kinds of let us say management of the transfers, and these also are usually quite closely tied to the kind of physical model that is there. So, let us take a look at how SCSI and fiber channel work together. So, in a storage network, as I mentioned, it is a block protocol. That means it uses the SCSI protocol to access data. So, if you are in a single desktop kind of system which uses SCSI, basically there is some kind of a flat cable that is used to connect disk to the host bus adapter, the agent for the computing system, okay, the storage agent. But if you want to do it across longer distances, then SCSI is not suitable, because it doesn't have, it has some, originally when SCSI came around, it didn't really have the notion of being able to interconnect longer distances. So, the solution that was adopted in later versions of SCSI, for example, SCSI 3 for example, or SCSI 2, was to use fiber channel or some other protocol like iSCSI, which again we will discuss later, as the protocol to encapsulate SCSI. So, what is fiber channel? It is a frame based protocol, and groups of frames in one direction is called a sequence, in both directions it is called an exchange. What is interesting about fiber channel is that it uses what is called zero copy send and receive semantics. sometimes called remote DMA transfers. What this means is that the network interface cards for the fiber channel, after some negotiation, they essentially keep track of the memory location of the buffer of the receiver. So, because they know the memory location of the buffer of the receiver, the DMA transfers that takes place across the network can directly deposit the transferred data directly into the memory of the recipient. So, you can essentially avoid other extra copies. And after one frame is transferred, again the network interface card for the fiber channel, it calculates a new location for the next frame, and it does it every time. So, therefore, it always can keep track of the location. And even if there is a loss of synchronization because of loss of sorry, made a mistake, even with the loss of frame, it turns out there is no loss of synchronization. Okay, basically because the commands that they exchange, they essentially specify all the details beforehand fully. Okay, and because of this, it turns out there is low host CPU utilization. This is in contrast with, for example, gigabit Ethernet, which went through a lot of difficulties in the beginning, because it turned out that there was a lot of copies going on, and you had to do a lot of re-engineering of the network stack so that the copies did not take place. And it was before the copies could be re-engineered away, the CPU was always involved in the copies, and therefore it used to have a very high CPU utilization. Okay. And for the same reason, because you are not doing any extra buffering, it reduces memory requirements for fiber channel NICs at these speeds. As I mentioned earlier, it uses grid based congestion control. We will look at it soon. So, diagrammatically, you can see the following. There is a buffer here in the NIC, there is another buffer in the NIC. This is, each is a frame. It turns out in fiber channel, the maximum size of a frame is 2012 bytes, and multiple frames is what is called a sequence, and multiple sequences is called an exchange. This is always in a single direction, this is bidirectional. Okay. And the important thing is that this particular NIC knows exactly the address of this buffer, where it has to be deposited in the application, therefore it can actually directly deposit it. Diagrammatically, you will see the layering as follows. At the lowest level is basically the optical communication. In the beginning, it started with let's say 1 gigabit per second or even lower, but nowadays 10 gigabit per second and 16 gigabit per second fiber channels is available. Okay. Because you are transmitting at very high speeds, to reduce possibilities of errors, they do a lot of encoding and decoding. There is something called 8-bit 10B, that means 8 bits of data is encoded into 10 bits, or you can also do 64-bit, 66-bit. So, there is a lot of encoding that happens because to reduce the chances of error, because you are transmitting at very high speeds. And we will look at this framing and control, the control flow aspect of it, especially soon. There is also common services. For example, it is possible that you can do encryption, etc. Of course, this FC3 typically nowadays is empty, nobody uses this typically. Okay. On top of it, you have SCSI. Fiber channel started in the beginning with supporting some protocol HIPI, the other protocols, but I am not going to go into them. It can also support other protocols like IP, for example. Okay. So, basically for us, what is interesting is SCSI, control flow, and the speeds themselves. The rest of it I think are certainly important, but I am not going to discuss them. These three things are basically what is called the physical layer, starting from this to this, okay. Framing and control and decode. Okay. Let us see how the mapping happens. We saw in the SCSI protocol that you have things like write commands, that is what the initiator tries to do. Then the target, after having allocated buffers, it says I am ready to receive your packets, so it sends a ready to transfer. Then the initiator sends the data, and then once the data transfer is done, then the target sends back a status. So these things have to be mapped to the FCP protocol data units. Okay. That's basically what I am calling as a map. Okay. So for example, there is a one-to-one correspondence, write command becomes FCP command. It's unsolicited command because the target, it has to come, it's the beginning part. Okay. So it's unsolicited, it comes out of the blue in some sense. Then there's something called SCP transfer ready, which basically means that the target now is saying that I'm ready to accept the data, and again once that happens, then the target again sends the data by encapsulating in FCP data protocol unit. Okay. And then again the target sends back using FCP. Other aspects of it is that this is per protocol event. You can essentially take a SCSI IO operation to be an exchange and each associated SCSI phase to be sequence, right. So this again that in a tabular form I have listed again. So IO operation is basically exchange, that means it's bidirectional. This is the request response primitives, that is there could be multiple let us say sequence units or frames that are sent to with respect to one let us say an IO operation, for example a write, and in turn the command is basically the SCSI command is mapped to this, the data delivery is mapped to this, the being ability to, sorry I made a mistake, the data delivery basically the target being ready to accept the data being sent is this transfer ready protocol unit, and the FCP data is what is the corresponding to the write data of the SCSI command, and the response FCP response is the corresponding response for the SCSI. Okay. So this is an example of a mapping for SCSI commands onto FCP protocol units. Again this is diagrammatic, one way this command goes this way, transfer ready comes back, the data goes this way, response comes back, and these are the two initiator and targets which are at the SCSI upper level protocol. This is a transport, and this transport can be, let us say, can be arbitrarily complicated because there can be arbitrary network sitting out here, and there is something called a port. Just like your IP address, you can have a port number and there could be another port number, and some routing also is done. Okay. So we will not get into too much in detail all these things, but there is a whole amount of infrastructure here which takes care of routing, it takes care of discovery. For example, how do you know that there is some target out here? Okay. So there's also issues about issues about security, issues about can this initiator actually access this particular network. So there's some notion of what's called login. That means that this particular initiator can actually access this thing. As I mentioned earlier, SANs are for a single client typically, unless you do something else application level to make sure concurrency is taken care of. So there could be multiple single clients which their applications are somehow ensuring that they don't interfere, but that means that each client should be somehow be able to get access to this infrastructure, and that means that there has to be some protocol in the beginning itself, and so there are some specific things called login procedures that have to be done. Again, I am not going to go into too much in detail about those things. Now just let's quickly look at why Fibre channel has been used extensively in storage. First, one thing to notice about Fibre channel is that they have quite a few varieties of class of service. You can have what is called a dedicated connection, ACK based connectionless service, connectionless without ACKs, and this class 3 is the one which is widely used. Okay. So you might be surprised to know why connectionless and without ACKs is the one that is used. It's used because Fibre channel is an extremely good medium. Its error rates are extremely low. Therefore, anybody trying to do ACKs etc., they are going to be slower than if you were to use it without ACKs. That's why the expectation is that since the error rate is so low, if anything bad happens, it will be handled at higher layers. Okay. So there are a few other classes also which I won't go into. Okay. Let us look at, as I mentioned, if you look at the previous one, we are talking about mostly connectionless and without ACKs. So, because there are no ACKs, that means that there is no inherent way in which you can avoid buffer overruns. So, that means that there has to be some flow control. Now, there are two possibilities. You can do flow control at the link to link level, or you can do it at the transport level, end to end. Okay. What I am talking about is, if you have a big fiber channel network, you can have what is called link level flow control. That means that you only, for every jump from one link layer device to the next link layer device, you have flow control. That is, it is happening in small segments, one segment at a time. But end to end, it is across the whole set of devices that are in between, routers, whatever that's there. Okay. So, of course, they also defined other models like full duplex and half duplex. And as I mentioned earlier, you need things like login, discovery, all those kind of capabilities. And this particular layer of fiber channel 5 FC2 handles all these issues. Okay. So, we will go more a bit into these details. So, in class 1, as I mentioned earlier, it supports end to end credit flow control. There is no buffer to buffer credit flow control. In order delivery is guaranteed, okay, guaranteed max bandwidth. So, this is the one which is, it takes a lot of trouble to make sure that your data that is sent is in the same order that was queued to it, sent to it, and also is making sure that across the whole fiber channel network, there is credit flow control, end to end credit flow control. And so, this is going to be the most difficult one to engineer for from the point of view of the fiber channel network. Okay, it requires a lot of infrastructure, a lot of that's hardware. Whereas the one which is common, as I mentioned, is this one. There is no end to end credit flow control. There is only between one there is a device, fiber channel device to another. That's it. Okay, and its upper level protocols have to take care of the actual flow control across end to end. Okay, that's what they have to do. In addition, no in order delivery is guaranteed. So, that's something you also have to worry about. Okay. Basically, the reason why people have storage systems in fiber channel typically class 3 is because it allows better use of fabric and bandwidth, because you do not have to do any hacking, etc. Okay. There is also another one called class 2. It basically has an end to end credit flow, but does not support in order delivery. Okay. So, but anyway, the most widely used is this one. So, we will not discuss other ones. Okay. There are other statistical model also is available if you want to use it. If there is some class 1 bandwidth not used, you can use it for class 2 and class 3. This is the some kind of statistical multiplexing kind of model. Again, the exception handling can happen at multiple levels. Okay. So, for example, if there is a frame that is dropped, okay, it might be done at the link level, it might be or it can be done at slightly higher levels. Okay. And there is also some other aspects. Basically, when the network comes online first, the very first time, the discovery aspects have to be also taken into account, and some of these issues also have to be done at multiple levels. Okay. So, here we are only talking about what happens when some packet that is transmitted gets lost. Okay. As I mentioned earlier, this is very rare, but it does happen, and so they have to be handled. If you are using, of course, the class 1 kind of models, then each of the fiber channel devices that are there in the fabric, they have to handle it in the hardware itself. And whereas if we use class 3, then some of the exception handling is done by some of the at the protocol level. Okay. Now let us see what is the issue with respect to credit based flow control. Now as I mentioned earlier, fiber channel, the medium of transmitting the data is fiber, which is basically optical fiber. And as you know, the speed of light is about 186,000 miles per second. Because of other issues like index of refraction, etc., the actual speed is about 100,000 miles per second. That is about 100 miles per millisecond. So if you have 100 miles per millisecond, now you can start thinking how it can actually impact your design if you are expecting some kind of round trip delays because of acknowledgements. Okay. So essentially the design of fiber channel has been to make the assumption that you can tolerate about a millisecond of delay, okay, because typically it has been designed for a single large data center. So you are going to be within 100 miles or so, okay, definitely, okay. So about a millisecond it's okay because you can do the round trip within a millisecond. So even if you add other things like latency of switches, routers, etc., right, instead of it at the most is about a millisecond, okay, it's only for example tens of microseconds, okay, it's not too much, okay. So if you assume that it's a millisecond or at the maximum 10 milliseconds, you will notice that the performance of fiber channel maxes out, okay. You can see this, for example, suppose you have what is called 64 credit switches, okay. So you have fiber channel switches, routers you might call it, or the link layer level. Suppose you have 64 credit switches, you are able to send one packet at a time, but you have to get ACK back, right. So you are able to get, you can send about 2112 bytes, but if you assume because of additional delays, let us say it goes, it can be as much as 10 milliseconds, essentially what you can do is you can send 2112 bytes into 64 by 10 milliseconds. So that is actually 13.5. If you make it to 1 millisecond, you can be 135 megabit per second. Okay. So if you are, of course, lower than that, you can be slightly better, but you can at the most do about 200 megabyte per second because of this. Okay. If you have something smaller, 16 credit switches, for example, your performance also decreases that much. Okay. So in a sense, your round trip delay has a very big important impact on the performance. It is true for TCP also, but it turns out that because of the way the flow control is done in TCP, you can by using bigger buffers, you can essentially do much higher throughputs than so. For example, people have done multiple gigabit per second transfers in TCP without any trouble, okay, across a wide area network. Whereas with fiber channel, it is not possible because the number of credits determines how much you can send, okay, and then you have to keep on waiting for the ACKs to come back. When the ACK comes back, then you get a chance to send one more packet, okay. So this is one important issue that is there in fiber channel, and so the fiber channel was designed in the late 90s when the kind of speeds we are talking about was rather high that time, therefore it wasn't an issue. But nowadays with the 10 gigabit Ethernet and those kind of speeds also becoming common and fiber being extensively used, the design aspect with respect to credit based flow control has been slightly problematic, okay. So again, to diagrammatically you can see the following. This is the initiator, this is the target, this is the transmit buffer. Basically the application has written some data into here, and then you want to send the data back to this target. As I mentioned earlier, the target has to send a ready signal back so that it can do it, and this signal has to percolate backwards, okay. So suppose there is some kind of routing, multiple fiber channel switches are in between, okay, a lot of switches are in between. That means that there is everybody has to, because they are all of these entities are talking fiber channel protocol, SCSI SCSI based Fibre channel, right. So that means that every time they receive it, they have to send back a ready, then only this guy can send something. So everybody also has the same situation, okay. That means that if I want to send something to here, one packet, then it is the sum of all the delays, okay. So in a sense, the number of switches that are there in between and the delays that are there for transmitting across this whole section of the switches, and if there could be some wide area network, let us say delays also, if you are really trying to encapsulate Fibre channel through some other protocols, then all these delays are going to be involved before I can get one packet back saying you can now send one more packet, right. And essentially this is what was the problem, and again I have illustrated here by saying that, for example, the buffer to buffer is between these two, end to is between this end and this end, okay. So all the delays essentially matter in Fibre channel. Suppose you want to do something better than this, okay. Suppose I want to write 512 kilobytes, and this is the initiator, this is the target, and basically I am going to this is going to be my first level Fibre channel switch out here. This is my, on the other side, this is going to be my first level Fibre channel switch, okay. So this is the, you can call it the initiator, this you can call the entry into the Fibre channel network, this is the exit from the Fibre channel network, and this is the target. So this can be a disk, for example, and this can be the application, HB, for example. So what we are talking about is, I do a write, then it has to traverse this Fibre channel network, it goes all the way up to this point, this write command, then the command, once it is received by the target, it will allocate some buffers and say I am ready to transfer. Again it has to percolate back all the way up to this point. Again, once the write command is, the transfer ready command is coming, then it actually can send the data. Suppose I am doing a 3 into 512 kilobyte transfer, so I send 512 kilobytes, it has to come back all the way. So this is for one 512 kilobyte, this was second kilobyte, this is for the third one, and then the status will come back. So you can notice that there is going to be these delays 1, 2, 3, essentially some kind of 4 round trips are involved, okay. Now if you are going to incorporate some wide area network in between, and somehow you are able to encapsulate the Fibre channel protocol inside it, then all these delays are involved. So your throughput is going to be quite small, it is going to be basically 512, like 1.5 megabyte divided by that 4 times round trip time, okay, it is going to be very slow, okay. And this basically is because Fibre channel has this notion of credit based flow control. You actually have to get the credits before you can send anything. In the beginning you can send something, but again once you have sent it, you have to get back the AX before you can, the credits have to be replenished before you can send it back, okay. So if this is the case, are you limited to this? Luckily, as I mentioned earlier, in SCSI protocol, you can introduce intermediate agents, right? You can also introduce intermediate agents here also, and we can do the following. I have the initiator, and then I basically have a special controller. I have a special controller here also, okay, which actually talks to the Fibre channel network, okay. So this is the initiator, this is the target. I have a special controller which is sitting in front of me, and it takes care of the transfer from this to this through some other protocol, okay. Let us say some highly optimized protocol that can do wide area network transfers efficiently, let us say that, okay. So what I am going to do is, when the initiator sends a write command, this special controller traps it, okay, and it pretends as though it is the target, okay, and so it sends back transfer ready. And since initiator and special controller are nearby, right, so this command can come back immediately and the data can be blasted at the highest speeds possible between these two entities, and there is some special protocol from going from here to here that can essentially take all the data and blast it back here. Okay, I'm sorry, there is some okay. So now what happens is that this command goes out here, and then the transfer ready happens, and once this data has come here, right, this special controller has already got the transfer ready from here. So what is happening out here? Basically what we are talking about is, once this write command comes here, okay, because it is going to both the places, this write command is sent to the target, and that the target essentially says, now I am ready, and this is going to be local. Okay, let's assume that the special controller and the target are co-located somewhere. Okay, because they are co-located, the minute the special controller gets this write command from this distance, through wide area network, whatever, this write command essentially is sent, is received quite quickly, and this target can respond immediately, right, as quickly as it can. Okay, and once this transfer ready is done, then this data that is sent in a bulk fashion, as fast as one can imagine, is possible across whatever special protocols you are using. This data can come here, and then this data is parceled out, segmented and parceled out to this target as needed. Okay, and because this particular special control and target are co-located, therefore we don't have any serious problems of trying to navigate this wider network round trip, that they will not be coming in the picture. Okay. So for example, what will happen is that this will take place very quickly, and then this status is sent back. Again, I should warn you that this particular picture has not been drawn to scale. So these time units are quite small. Okay. So basically what's happening is that there's only going to be only one round trip delay. You send it out here, and then you get back the status comes back, and therefore your throughput can be that much higher. Okay. So so basically what we are saying is that because you can virtualize SCSI endpoints, and therefore you can incorporate multiple devices in between. Okay, even if there are some problems with the protocol, sometimes you can work around it, but it requires some special engineering to make this happen. Okay, and again, we will next class what we will do is we will study how TCP/IP does this in a slightly different way. It's not going to, it's not a credit based flow control model. Okay, and so that requires some other types of engineering, and it turns out that because TCP/IP, it can suffer losses. Because it can suffer losses, it requires a different kind of flow control, and that creates certain complications for zero copy. Okay. Here it turns out that I can do zero copy quite well, because the protocol actually keeps track of the memory, it can essentially do remote DMA, but TCP has a hard time doing zero copy kinds of transfers. It's possible to do it, but it's not so easy, and so there are both plus and minus points in these cases. So in TCP essentially you need higher performance devices so that you can do all the TCP protocol processing, whereas in the fiber channel you may not need that high end systems. Okay. So there are the protocols that you choose for storage, typically there are a lot of implications across the layers, and that's something you have to worry about. Okay. Again, we have not talked about other aspects like security and other aspects. All these things also have very big impact on the performance of the system. So in summary, basically it turns out fiber channel is an effective protocol in the data center, but as we discussed before, it is not that suitable for wide area network. We need to do something about encapsulating this particular protocol for high bandwidth, and so it turns out that fiber channel nowadays is also going through some other transformations, basically the idea is to see how you can encapsulate fiber channel in 10 gig Ethernet, and it's called fiber channel over Ethernet, FCOE. Okay, that is also something that is taking place on a wide scale. I think with this I am going to stop today's class. I will in the next class I will look at suppose I use internet as a way to deliver SCSI, how that can be done.